I am glad to present our work, Planar, Learning Planar Primitives for 3D Plane Recovery. First of all, I will briefly introduce the related background of our work. Recovering 3D planes from a single image is a fundamental problem in indoor scene understanding, supporting applications such as augmented reality, SLAM, and robot navigation. However, much of the recent progress mainly benefits from the evolution of 2D vision architectures, while ignoring that planes are inherently 3D geometric structures. So the key question is, how can we fully leverage 3D planar priors to guide perception beyond 2D predictions? Our inspiration comes from Gaussian splatting, which shows how 3D primitives can act as the building blocks for scene reconstruction. Following this idea, we treat planes themselves as 3D primitives and design a system that can reconstruct, aggregate, and render these planar primitives end-to-end. Thus, we propose Planar, an end-to-end framework for plane reconstruction, aggregation, and splatting. The system explicitly leverages 3D geometric reasoning combined with online planar primitive reconstruction from a single image. This method consists of 4 main stages. We start from an input image and extract multi-scale features using an image encoder. These features interact with dense plane queries through attention blocks. The system iteratively refines these queries parameters toward a coherent 3D representation. Refined local plane queries are aggregated into global plane queries, representing final plane instances. We use dot product similarity to estimate the probability that each local primitives belong to a specific plane instance. Finally, we splat planar primitives onto the image plane to render depth maps and instance masks, which will be used for supervision from both geometry and segmentation. During splatting, we design a new planar kernel. Compared with 2D Gaussian kernel, the planar kernel exhibits a flatter distribution, much better matching the structure of indoor planes, such as the walls, floors, and tables. This structural alignment improves both training stability and geometric accuracy. We evaluate Planar on 2 popular public datasets. Our method achieves state-of-the-art performance across multiple metrics. The visualization results show that our prediction align closely with ground truth in both segmentation and depth. Compared with PlaneRectR, our segmentation results demonstrate better adherence to actual geometric structures, indicating stronger geometric awareness. Ablation studies validates the effectiveness of our core designs. The planar kernel consistently outperforms the 2D Gaussian kernel, confirming its suitability for indoor scenes. Since we initialize primitive attributes with pre-trained models, another set of results show that depth priors contribute more significantly to improving aggregation accuracy. However, there are still 2 major limitations. Our method relies on pre-trained models to provide basic geometric structures, which increases memory use and inference latency. And secondly, since the training set mainly contains short-range depths, Planar tend to misclassify distant planes as background. To summarize, we introduce Planar, a novel framework that reconstructs 3D planes from a single image by learning planar primitives with explicit monocular geometric priors. our approach achieves state-of-the-art performance on benchmark datasets. As for future work, we plan to extend PlanRS to multi-view settings to enable more robust reconstruction with better generalization ability. Thanks for your attention.